Welcome to an introduction to propositional and predicate logic. It's an important topic because logic is the basis of all mathematical reasoning. In order to understand a math proof or an argument, you first have to understand how logic is written, and that's my goal. My goal is to get to the point at which we can understand and write a logical argument. The curriculum consists of 19 works. The first 9 will introduce propositions and truth tables. From 10 to 19, we will introduce predicates and quantifiers. Hopefully, by the end, we will be able to write a logical argument. It comes with an accompanying PDF. I encourage you to use it because it does two things. For one, it allows you to try the works first, and then you can watch the video afterwards. And for two, it has a series of exercises which you can use at the end to assess your understanding. I apologize that the video is long. It's 1 hour long, and I talk very slowly, so please feel free to watch it at double time or quadruple time if you wish. Propositions are statements that declare a fact. That is, they are either true or they're false. So which of these are propositions? The twin birth rate has risen 70% since 1980. That clearly declares a fact. So that is, yes, that's a proposition. Square root of 2 is an irrational number. That clearly is a proposition. It happens to be true. Number 3, 9 is a prime number. That is a proposition. It just happens to be false because 9 is a composite. X plus 1 equals 2. Now this one is not a proposition. We cannot determine its truth value unless we know what x is. So this is more like a propositional function or a predicate. Okay, propositions are combined into compound propositions. Usually we use logical connectives, and there's also the operator, the negation. So we might write the negation like this. This is how I normally write it. There are other ways, but an example would be not P, where P is the proposition. The conjunction is written like that, and you might say P and Q, where P and Q are propositions. The disjunction is written like this, P or Q. Implies, this is the conditional, which is represented by an arrow, and you might say if P then Q, and in this case we call P the hypothesis or the antecedent, and we call Q the consequent or the conclusion. The biconditional is written with a double arrow. You might say if and only if, like P if and only if Q, or you might say P is necessary and sufficient for Q. Find the negation of the proposition. This lesson has exercises at the end. First, we would have to define our proposition. So we could say, let the stated proposition be P. Then we just apply the operator, not P. You could write, let P be the proposition, and then in quotes, this lesson has exercises at the end, but this should be good enough. You could, of course, so this states it is not the case that P, or you could be more colloquial and say, this lesson does not have exercises at the end. Okay, so let's make a truth table for not P. Truth tables are basically lists of all the truth values of a proposition or compound propositions. So if we were to do a truth table for not P, we first need a column for P, and then we'll have a column for not P. And P has two options. It can either be true or it can be false. And the negation of P is simply the opposite of that. And that's it. Okay, so let's make a truth table for the biconditional. The first thing to note is that the number of rows in a truth table increase exponentially. So if I have one proposition, the number of rows would be 2 to the power of 1. If I have two propositions, the number of rows would be 2 squared. If I have three propositions, the number of rows would be 2 cubed. So it just keeps going and going. So the number of rows for a biconditional that has two propositions will be 4 rows, sorry. The number of columns we'll have a column for P, we'll have a column for Q, and then we'll have a column for the biconditional. So P and Q, the options are P can be true, Q can be true, or P can be true and Q can be false. P can be false, Q can be true, or they can both be false. So in order for the biconditional to be true, P and Q must have the same truth value. So in row 1 and row 4, they have the same truth value, so the biconditional is true. In row 2 and 3, they do not, they differ, so the biconditional is false. Okay, so we are going to use a truth table to verify the logical equivalence, which is this symbol here. That means logically equivalent. The logical equivalence of the commutative laws. So the disjunction in column 2 is true if P is true, if Q is true, or if both are true. So anywhere you see a true in the first two columns, this will be true. It would be the same if we replace P with Q, if we switch them. Now the conjunction, P and Q, it's actually better to look at this in terms of it being false. So if P is false, if Q is false, or if they're both false, then this is false. So anywhere you see a false, this is false. And if they're both true, then it's true. And we would apply the same reasoning to when we switch P and Q. Okay, now what it's important to note is that these columns are the same, and that means that they are logically equivalent. These are the same, so they are logically equivalent. Okay, so now we are asked to verify one of the rules of inference, and we're going to do that using a truth table. So how many rows are we going to need? Well, there's only two propositions, so we need 4 rows. How about the columns? Well, we're going to have a column for P, a column for Q, a column for P implies Q. We'll have a column for P and P implies Q, and then we'll have a column for this whole antecedent and the consequent. So first, in this column, the conditional, the only way in which that can be false is if P is true and Q is false. We're saying P implies Q. So if P is false, then by default this will be true. So anywhere that there is a false in P, these first two, these last two rows, this will be true. Okay, let's find a place in which P is true and Q is false. That only happens in row 2. So it's going to be false there. And then if both are true, of course, the conditional is true. Now, with this next column, what we are doing is we are actually comparing this column and P, this column. So remember, a conjunction is best to look at in terms of when it's false. If either of them are false, then it is false. So it will be false in row 2, 3, and 4. And true in row 1. So this last column, what we are actually comparing, that this conditional, we are comparing that column with Q, that column. And remember, the antecedent must be true and then Q false in order for it to be false. So the only place that the antecedent is true is right there. So that's the only option, that's the only possible row in which it can be false. Q must be false there, but it's not, it's true. So that happens to be true. And everywhere else, it's going to be true. And that right there is a tautology. When you see a column of T's, a column of truth, means that it's a tautology. And tautologies, they're very useful for constructing arguments. We will see later on. One of the more pleasant aspects of propositional logic are logic puzzles, so I threw one in for fun. Imagine you're on an island, and there are two types of people, knights and knaves. Knights always tell the truth, and knaves always lie. So if you meet two people, A says B is a knight, and B says the two of us are opposite types. To solve this, you would assume that, let's start by assuming that P is true. So if P is true, then that means that A is a knight. So when A says B is a knight, then he's telling the truth, and P implies Q. So if Q is true, then that means that B is a knight, and when B says the two of us are opposite types, he is telling the truth, and that means that P cannot be a knight. That means that P must be false. But that's a contradiction, so that doesn't work. So let's assume that not P is true. We'll assume that A is a knave. So that means that A says, when A says B is a knight, he actually means that B is a knave, because he's lying. So not P implies not Q. So if not Q is true, then when B says the two of us are opposite types, he's actually lying, and they are the same type, which means that not Q implies not P. And that works. That's the solution. A and B are knaves. Okay, so let's find the converse of the inverse, converse of the converse, and converse of the contrapositive. So the inverse simply negates the antecedent and the consequent. The converse interchanges the antecedent and consequent, and the contrapositive applies the inverse and the converse simultaneously. So let's do that. The inverse of the initial statement, so the initial statement is a conditional if P then Q, and the inverse would simply be not P implies not Q. The converse would be Q implies P, P, and the contrapositive applies both, so it would be not Q implies not P. So now we're going to take the converse of each of those statements. So the converse interchanges the hypothesis and the conclusion. So it would be not Q implies not P, which notice that is the same as the contrapositive. So the converse of the converse would be P implies Q, and that is the same as the original statement. The converse of the contrapositive would be not P implies not Q, and that is the same as the inverse. The point at which propositional logic ends and predicate logic begins is when propositions are converted to predicates. To convert a proposition to a predicate, all you have to do is replace the proposition's nouns with variables. So predicates are essentially propositional functions, and predicate logic is all about converting those functions back into propositions, and there are two ways that we do that. The first way, we assign values to the variables so that you can perform the function and determine its truth value. The second way would be to use quantification, and this assigns either universal or existential properties to the predicate. There are other quantifiers, but those are the only two I'm going to be concerned with here. So the first one would be, so for all, so this is the universal quantifier, for all x, p of x. So this means that there is a property that holds for every single value of x in the domain. So this would be true when p of x is true for all x in the domain, and it would be false when you can find at least one x in the domain for which p of x doesn't hold. So the existential quantifier, written with the backwards e, this would stand for there exists an x such that p of x. So this means that there is a property that holds for at least one value of x in the domain. So this would be true when p of x is true for at least one x, and it would be false when you can find that every single x, p of x is false. So if p of x is false for every single x, then this whole statement, the existential quantifier, is false. So in general, it's easier to prove the universal quantifier false by finding an example of it being false. And of course, it's easier to prove the existential quantifier true by finding an example of it being true. Having said that, in many proofs, it is often the case that quantifiers are often completely implicit or not even shown at all, and so that's definitely something to look out for. Okay, so there's not much to this one. We will be converting predicate to a proposition by substituting values for the variables. So with the first p of 1, 2, all we would do is substitute x into x, or substitute 1 into x and 2 into y. So 1 plus 2 equals 4, which happens to be false. And in this case, we would do the same thing, which happens to be true. So this universal quantifier, let's see if it's true for all real numbers. If we plug in a -1, then that'll still be true. Like -1 squared is greater than or equal to -1. If we plug in a 0, 0 squared is greater than or equal to 0. If we plug in a 2, it's still going to hold. So we can't seem to find an example with integers, but how about fractions? Well, that's not true. That's false. And with the universal, we only need to find one example or one counterexample to prove that it's false. How about for the integers? Well, we kind of already shown that, right? We've seen negatives, positives, 0, so that is true. The universal quantifier in this case is true for integers, but not true for all real numbers. We have a predicate in which the domain is all integers. So let's assess the truth value of these specific cases. So in the case of 0, 0 equals 0 squared, and that happens to be true. In the case of 1, 1 equals itself squared, so that happens to be true. In the case of 2, 2 equals 2 squared, well, that happens to be false. Negative 1 also is false. Now how about in the case of the existential? So in the case of the existential, all we need to do is find one example of it being true to prove that it is true. So we've already done that, A and B. I'll just say C, A, and B. It's true. In the case of the universal, we just need one counterexample to prove that it is false. And we've done that in C and D. So that is false. So in this particular case, the existential quantification of P of x is true, and the universal quantification of P of x is false. Okay, so let's express the existential and universal without quantifiers. We have integers between -1 to 1 domain, so that is our domain. And in the case of the existential, it can be true for it is true for at least 1x. So that means it could be true for -1, or it could be true for 0, or it could be true for 1. In the case of the universal, this is true for every value or every single x in the domain. So that means it will be true for -1, and it'll be true for 0, and it will be true for 1. In this case, it is true for every single value of x in the domain except for 0. So it will be true for -1, and it will be true for 1, with 0 omitted. Recall that two statements must have the same truth value in order to be logically equivalent. We showed this before, but what we did was we used a truth table. In this case, we're not going to do that. We are just going to reason through it. So the negation of this universal, that will be true if and only if its negation is false. Okay, so the only time that this is false is if there is an element in the domain for which P of x doesn't hold. So there must be an element in the domain for which P of x is false. Okay, so when is P of x false? Well, P of x will be false if its negation is true. Okay, so what does this mean? This means that there must be, this means that there will be an element in X, like an element in the domain for which the negation of P of X is true. And that will hold if we could say, so the negation of P of X holds if there exists an X for which the negation of the predicate is true. Okay, so what have we shown? We started off with the negation of a universal being true, and we ended up with an existential and the negation of its predicate being true. So what we showed was therefore is logically equivalent and we are done. In a similar way, you can try and reason through some of these statements. Number 1 and 2, actually, number 1 is the counterpart to what we just did. Number 2 and 3, those are called De Morgan's laws, and they show that the negation of an and statement is an or statement, and the negation of an or statement is an and statement. Number 4 to 7, they show that universal quantifiers, they distribute over conjunctions like an and statement, but they don't distribute over an or statement, a disjunction. And the opposite is true of the existential quantifiers. So in the case of the existential, they distribute over disjunctions, but not over conjunctions. 8 and 9, that they show you how to negate consecutive quantifiers. Okay, we just saw that to move the negation to the predicate, we have to change the universal to the existential quantifier. And so to negate this statement, we could move the negation to the predicate, change it to the existential, and then we could make it more succinct by stating x squared is less than or equal to x. And that's it. Oh, this is fun. So what is the truth value of the universal all dots in the box are pink? What do you think? Think about this for a while, actually. It's a good idea to think about this first. So there are no dots in the box, but let's reason through this. So this statement means for all dots P of x, right? And where P of x would be the proposition that the dots in the box are pink. But there are no dots in the box. So let's think about it this way. The statement is false if its negation is true. Okay, so let's negate it. Negation of P of X. That is logically equivalent to this. Okay, so this should be, there exists an element such that, or I'll say this, there exists a dot in the box that is not pink. That's what this means. That's what this means. Is that true? There exists a dot in the box that is not pink? This is trivially false, right? Like, there definitely does not exist a dot in the box. So this is false. That is false. So what does that mean? That means that this, which is logically equivalent to it, is false. And then its negation must be true. So that means that by default, the statement all dots in the box are pink is true. That's weird. So the original statement is true by some default. We actually have a name for this. We call it vacuously true. Anyway, I like that. Okay, let's translate the statement into a logical expression. A student in your class is failing. So we have to define our propositions first, and of course the domain. So we might define it like this. Let P of X, Y be person X is in class Y. So person X is failing. That's an S. Okay, so let's assume that the domain is classmates. So if we assume that the domain is classmates, then, well, this is easy. There is a person such that they are failing, right? There's a person in the domain, which is classmates, that is failing. This is, I should say, the domain is classmates. But let's change the domain. Like, we're not given a domain, so we can choose it. Let's change the domain to schoolmates instead. If I can spell. Schoolmates. So in that case, we would have to say there is a person in which P of X and the Y would be, you know, your class, our class, your class. And Q of X is true. And that would be it. We would have translated it. Okay. So let P be it is raining. Let Q be I will go out to play. Show that P implies Q or P leads to Q. For some reason, I believe that should be and P, not or. That seems wrong to me. That can't be what it... That should be and. I'm pretty sure that should be and. Otherwise, it wouldn't necessarily... Yeah. Okay, so let's change that. So now we are asked to make an argument. An argument... Okay, so an argument is a series of premises that culminate in a conclusion. So premises can be either assumed or derived, in general, you start an argument with a few assumed premises and then use either mathematical axioms or rules of inference, and you derive subsequent premises, finalizing in some conclusion. Well, in this case, we would say that we would have a premise, which is if P, then Q. Oh, I don't need brackets. So that would be a premise. So 2, we would have P. That would also be a premise. An assumed premise. And then we could have a conclusion. Therefore, Q. And that would be a derived conclusion from 1 and 2. So this reasoning has a name. It's called modus ponens. We have already seen it in a truth table. What did we show? We showed that, we showed exactly this. Well, I'll write it out. We showed if P implies Q and P, then the whole thing will imply Q. We showed that that's a tautology earlier. So this reason is valid because its form is valid. So this form. So the reasoning is valid because this form is valid. It's it follows the modus ponens form. So it still might lead to a false conclusion. Let's say that I hated the rain or was afraid to get wet. Well, I'm not going to go outside. And so my premise 1 would be false. And so my conclusion would be false. Premise 2 would still be true. It could still be raining. But here are a small few of the rules of inference that are common. So it is in the PDF, but just in case you don't have it, I wanted to show you so that you could take a screenshot. So I'd like to draw your attention to universal instantiation. So this applies if a property is true for every member of a set, then you can assume that it is true for any member of the set. This is kind of foundational to deduction and how we think. You might say something like, all Celts speak Cornish, therefore Paul the Celt speaks Cornish. Universal generalization applies if you take an arbitrary member of a set and you show that some property is true, then you can assume that property applies to any and every other arbitrary member. You might say, any even integer is divisible by 2, therefore all even integers are divisible by 2. Okay, now we know enough to write an argument. And that's what we're going to do. So there'll be one rule. We cannot use any rules of inference implicitly. So we'll have to state them all. And the first thing we'll do is we will define all of our propositions, which I've already done here. And that should be all that we need. I will shrink this a bit so that we can see. Okay, so step 1, what we're going to do is we will write our first premise, which will be that all x for all x that are in school, they can take, that have taken a computer science course. So for all x, q of x implies p of x. And that will just be an assumed premise. Okay, now we are going to, because we have the universal, we can use universal instantiation and pull out a member, which in this case will be Bob. So Q Bob implies P Bob. That is universal instantiation from 1. And now we are going to have another premise, which will be, so if you have taken a computer science course, then you're permitted to take discrete mathematics. So for all x, if p of x, then r of x. That will be an assumed premise. Then we will use universal instantiation again to pull out Bob. So P Bob implies R Bob. From 3. Okay, now we can combine 2 and 4 together. So we can go from Q Bob to R Bob. Q Bob implies R Bob. And let's go find out what that is, which I have it here. That is hypothetical syllogism, that form right there. We are using 2 and 4. 4. Okay, 6. Well, we need for Bob to be true, for Bob to actually be at the school still. So we will have a premise of Q Bob, which will just be an assumed premise. And then we can say, therefore, R Bob, which is modus ponens. From 5 and 6. And we've done it. That is, we've constructed an argument, which was the goal of this lesson.